In this section, we're going to be talking about reversible reactions. So some reactions don't go to completion as we have assumed. They might be reversible. This is a reaction in which the conversion of reactants to products and the conversion of products to reactants can occur simultaneously. So if we have this reaction here where SO2 and O2 makes SO3 in the forward direction, we also have the possibility where the SO3 can reverse to decompose into O2 and SO2. So the two equations can be combined into one for simplicity's sake by using a double arrow, which will look like this. You'll have an arrow going to the left and an arrow going to the right. You may have seen these before on some of your test questions. You may not know what it means, but this is what it means. It just means it's a reversible reaction where the formation of the products is just as likely as the products decomposing back into the reactants. So a chemical equilibrium occurs when this happens, and no net change occurs in the actual amounts of the components of the system. The rates of the forward reaction are equal to the rates of the reverse reaction. The concentrations may not be equal. They could be very heavily favored for products or reactants, but the concentrations remain constant throughout the entire reaction. This is a very popular Regents question that trips up a lot of kids. You just need to remember the concentrations are constant and the rates are equal. So think of that alliteration. Concentrations constant and rates are equal. So this was discovered by a man named, or studied by a man named Henri Le Chatelier, and he called it Le Chatelier's principle. So he was a French chemist, and he studied how equilibrium position shifts as a result in changing conditions. So his principle says if stress is applied to a system in equilibrium, the system changes in a way that relieves the stress. So there are a couple of different things that can be stresses on an equilibrium position of a reaction. So one is concentration, temperature, pressure, and that's it. So first let's look at concentration. So if you add more reactant, you produce more product. And if you remove the product as it's formed, you also produce more product. So let's look at an example here. So carbon plus oxygen makes carbon dioxide and 393.5 kilojoules of energy. So if I added more reactant, so if I was reacting this carbon and oxygen and I could pump more carbon into this reaction, the reaction would progress in the forward direction and produce more carbon dioxide. But as the carbon dioxide builds up, the reaction is going to slow down or stop. So if I remove this carbon dioxide, if I had a way of siphoning the carbon dioxide away from this reaction as it was being formed, it would also shift the equilibrium position to the right and keep producing more product at a faster rate. Next is temperature. So increasing temperature causes the equilibrium position to shift in the direction that absorbs the heat. But an easier way to think about this is just treat the heat as if it's a chemical that's just a normal part of the reaction. It's just part of the equilibrium. So if it's a thermochemical equation like this, it's the same equation, carbon plus oxygen makes carbon dioxide and 393.5 kilojoules. This is the heat that's being produced in this reaction, and it's on the right-hand side of the reaction. So if I add something to the right-hand side of the reaction, like if I added more heat, the reaction will shift to the left. If I removed heat, that's like taking something away from the right-hand side. If I removed heat, the reaction would shift to the right to produce more product and ultimately more heat. The third one is pressure. So changes in pressure will only affect gaseous equilibria. So the caveat here is every single part of the equation has to be a gas, or changing pressure will do nothing. So when you change the pressure in a gaseous equilibrium, if you increase the pressure, it will usually favor the direction that has fewer molecules. And the reverse would be true if you decrease the pressure. So let's look at this example here. N2 plus H2 makes NH3. So if I pressurize this whole system and I am being asked which way will the reaction shift, to the right or the left, First thing I need to do is check to make sure all the components of this system are gases. So I have a gas plus another gas makes a gaseous product. So yes, this is a gaseous equilibrium. So next what I need to do is count moles. So the the notes here says of the direction that has fewer molecules. Now there's no need to convert from moles to molecules because it will stay the same. Just count the moles. So on the right I have 2 moles of NH3. On the left I have 3 moles of H2, and there's no number here but it's really a 1. So I have 4 moles of reactants on the left and only 2 moles of products on the right. So if I pressurize the system, which way will the reaction shift? It'll shift, of course, to the right, towards the side that has less molecules or less moles. So you can memorize those 3 things. It wouldn't be impossible to do, but let me teach you a little trick to help you answer Le Chatelier's principles questions. And I call it the teeter-totter trick. So you've probably all played on teeter-totters as kids. You have a little fulcrum point here that pivots. You have a board that the kids sit on, and it can move back and forth depending on differences in weight. So a reaction that's at equilibrium is at balance. So if you have a reversible reaction, it's like an equally balanced teeter-totter. But if I add something to the right, like if I add another kid to the right, or if I add more product, that's going to upset the equilibrium. And the teeter-totter will tilt to the right. So you answer the question by asking, which way must the teeter-totter move in order to bring it back to equilibrium? Which way will the reaction have to shift to bring the chemical equation back to equilibrium? In this case, the reaction would have to shift to the left to balance it back out. So as it shifts to the left and produces more reactants on the left-hand side of the arrow, you are relieving that stress of the extra products on the right. So let's look at an example here. Which way would the equilibrium position shift if we add more NH3? So here's my reversible reaction, and it is at equilibrium because I have a reversible reaction here. And they're asking what's going to happen if we add more NH3. So NH3 is on the left. That's like adding a kid to the left-hand side of this teeter-totter. The teeter-totter will tilt to the left and get out of balance. So Le Chatelier's principle says that the reaction is going to shift in a way to relieve that stress. So the reaction will shift to the right to bring it back into balance. Now shifting to the right means that the NH3 that we're adding and the O2 that's already in there are going to start reacting more frequently and more rapidly. When that happens, we're going to produce more products. We're going to make more nitrogen monoxide, and we're going to make more water vapor here, and we're going to make more heat as we shift to the right. Here's another one. Which way will the equilibrium position shift if we add more heat? Remember, we treat heat as if it's just another kid on the teeter-totter. In this case, heat is on the right-hand side of the teeter-totter. So if I add more to the right, the equilibrium position will be not in balance, and the teeter-totter will tilt to the right. So which way will it shift to bring it back into balance? And of course, we'll shift to the left. These two are going to start combining more frequently with this extra heat, and they are going to react to produce these reactants on the left, and it will come back into balance as we shift it to the left. So what if we removed nitrogen monoxide gas as it's formed? So nitrogen monoxide is on the right, so it's like taking a kid off the right-hand side of this teeter-totter. Now the left-hand side will have more weight, and the teeter-totter will tilt to the left. So the reaction will have to shift to the right to bring it back into balance. How about if we added more pressure to the system? So if it's a question about pressure, the first question you ask yourself is everything a gas? Gas, 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 gas. Yes. So next what we need to do is count atoms, or count moles I should say. So on the left hand side I have 4 moles of NH3 and 5 moles of O2. So that's 9 moles of reactants on the left. On the right I have 4 moles of NO and 6 moles of H2O. So that's 10 moles of products on the right. So if I increase the pressure, the reaction will have to shift to the left because the left-hand side has less stuff. If you ever have a situation where the amount of moles is equal on the left and the right, then pressurizing the system will do nothing, in case you were wondering that. Okay, so yes, of course it'll shift to the left because there's less moles or less molecules on the left. Okay, so in summary here, at equilibrium, the rates of the forward and reverse reactions are equal. Like I said, that's a very common question in and of itself. That's just something you need to know. The concentrations of reactants and products are constant, but the amounts aren't always equal. They can be very heavily favored in one direction or the other, but the concentrations stay constant throughout the course of the reaction. Le Chatelier's principal questions will ask you about the direction of the equilibrium shifts when stress is applied to the system at equilibrium. And this can be a very challenging question. It usually throws kids on the regions quite often. But if you remember the teeter-totter trick, this should be no problem. The system will always respond in a way to relieve the stress that is applied. So use that teeter-totter trick and ask yourself, which way will the teeter-totter move after the stress is applied, and then therefore which way will the reaction have to shift to bring it back into balance. And remember, an increase in pressure only affects gaseous equilibrium. Every single component in the equation has to be a gas. If one thing isn't, the reaction will not shift one way or the other. But if everything is a gas, the reaction will shift in the direction that has less gas molecules.